Today we are going to see about analog to digital converters and digital to analog converters. Both A to D converters and D to A converters are used in transmitter side as well as receiver side. Usually our information carrying signals are in the form of current, voltage, temperature, pressure, which are in the analog form. If we transmit this analog form into the digital signal, we have a better accuracy and a low interference signal. For that we are using A to D converters in the transmitter side. Likewise we are using a D to A converters in the receiver side for recovering the original information signal. There are different types of A to D converters and D to A converters. Before going to the different types of converters, we have to know about the process of conversion. So first the analog input is given as an input to the anti-aliasing filter. The anti-aliasing filter is nothing but the low pass filter. It will block the high frequency component and allows the low frequency component. The low frequency component is again given to the sample and hold circuit for converting the analog signal into the digital signal. Then the digital signal is transmitted over the communication channel to the receiver side. In the receiver side, the digital signal is again converted to the analog form to recover the original information. In sample and hold circuit, the analog signal has to be taken over to the sampling process. In the sampling process, we have to take the samples of the analog signal at the regular time intervals, and then the sample have to be quantized and round off to the nearest voltage level for the transmission. So the sample and hold circuit process are carried out using the analog switches. There are two types of analog switches. First one is the shunt switch and the another one is the series switch. In shunt switch, we are connecting a FET transistor parallel with the resistor RD. By giving 0 voltage to the the FET gets on and we get Vout output as 0, while we are giving more negative voltage for the gate terminal. The FET will disable and the Vout output is equal to the input voltage. As like series switch, the FET transistor is connected in series with the RD resistor. By giving the 0 voltage to the gate terminal, the gate transistor will get enabled and the Vout output is equal to Vin. While giving more negative voltage to the gate terminal, the Vout output is equal to 0. The next one is the high-speed sample and hold circuit. This circuit consists of FET transistor and the capacitor connected between two op-amps. By enabling the FET transistor, the capacitor will charge us up to the incoming voltage and produce the constant voltage until it reaches the second sample points. The next one is the analog to digital converters. Here the input is an analog input. The ADC converter will convert the analog input into the digital form by binary digits 0s and 1s. Before going to the types of the conversion types, we have to know the resolution and the quantization error. So resolution is defined as the ratio of change of value of input voltage Vi needed to change the digital output by 1 LSB. By increasing the number of bits, we can get finer resolution and smaller quantization error. This is called the quantization error. So in A to D converters, we are having 6 types. The first one is the single slope and dual slope, successive approximation type, flash type, delta modulation and adaptive delta modulation. The first one is the single slope ADC. Here we are using one op-amp which will act as a comparator and AND gate, ramp generator, timing and control circuit, counters, latches and the decoders, and finally an LCD display. For example, we are having an analog input voltage as a 2 volt, another ramp generating input voltage as a 0 volt. When comparing input voltage and the ramp voltage, we are having a 2 voltage in the Vn input, so the non-inverting input is higher here, so we will produce positive voltage in the output of the comparator. So AND gate will enable and produce 1 in the output of AND gate. The 1 voltage will go to the counters and the counter normally in a reset position. So after the one output from the AND gate, it will count one step forward So now the latches will have a value of 1. The same 1 will be digitized and displayed in the LED display. Again, in the second step, the comparator will compare the 2 voltage and the 1 voltage from the RAM generator. Now also the analog input voltage is higher, so again it will produce 1 in the comparator output. Again the AND gate will produce 1 in the output. The counter again moves forward to the 1 step. Now it counts to the step of 2. So 2 will be displayed in the LED display. So when the RAM generator voltage is higher, the comparator output is 0 and the AND gate produces 0 voltage. So the counter will stop the counting process. So the 2 will be displayed in the LED. Type is the dual slope A to D converters. The circuit is same as like that single slope ADC. Before the comparator we have to add integrator circuit. The integrator circuit having two inputs, one is the analog input, another one is the reference voltage. By using the switches we have to connect the input which is Vi or a minus Vref. Here we are using two cases here. In the first case the switch is connected to the analog input, while the integrator receives the analog input plus Vi. The integrator output will be in the sign of negative. So the output of the integrator will be in the terms of minus 1 by RC integral of Vi dt. So the same minus Vi is given as the input to the comparator. The comparator will produce the positive sign in the output of the comparator. So the AND gate will enable and the counter will move one step forward. So while considering second case, the switch will move on to the minus V reference voltage. Now the integrator will produce the plus Vref in the output, that is minus Vref will be converted into the plus Vref in the output of the integrator. Now the comparator output moves to the negative voltage and the AND gate will be disabled and produce the 0 voltage in the AND gate output. The counter will stop the counter. So we will get the equivalent binary form of the given input voltage. The second waveform, we are seeing the waveforms. While giving the plus Vi voltage, we will get a minus Vi in the integrator. So it will produce the ramp down signal. While giving minus Vref voltage, the ramp up signal in the output of the integrator. Next, the third one is the flash A to D converter. The flash A to D converter is also called as fastest conversion of analog to digital form. Here we are using an comparators and the encoder. The comparator will have two inputs. One is the analog input and another one is the reference voltage. The analog input is shared between the all comparators. So the number of comparators will be decided by the number of bits. If the number of bits is 3, means 2 power 3 8, 8 minus 1 7 comparators we have to use. The 7 comparators will have an analog input voltage and the reference voltage. The output of the comparator is given to the encoder. In the output of the encoder we will have as 8 bits from LSB to MSB. So this is the faster type of A to D converters. The next one is the successive approximation type. Here we are using comparator, successive approximation register and the D to A converters. The comparator will compare the input analog voltage and the output of the DAC. The output of the comparator is given to the successive approximation register. In the next slide we will have to know the process of the conversion. Now we are considering the analog input voltage as 5.2 voltage. Already we are having a 4 voltage in the successive approximation type. So the digital value stored in the register is 100. So in the first step we have to compare the incoming voltage with the register voltage, that is 5.2 must be compared with the 4 voltage. So if the 5.2 is greater than 4, means we have to move the process to the downwards, that is S condition, by making the B2 bit as 1. So now the B2 bit will converted into the 1 bit. The second condition, we have to check the condition with the 5.2 is greater than 6 or less than 6. Now the 5.2 is less than 6. We have to move to the no condition by making the B1 bit as 0. Now the value stored in the register is 5, that is 101. Now we have to compare the incoming voltage 5.2 voltage with the 5 voltage. Now the 5.2 voltage is greater than 5 voltage. So now we have to move the B0 bit to the 1 condition. So finally we will get digital output as 101, that is approximately a digital conversion of the given analog input voltage.